A warm good morning to one and all. Welcome back to the fourth day of ATAL FPP program. We'll now be starting off with the first session of the day. The first session is an invited talk on the topic Security Challenges in IoT, Malware Detection, given by Dr. Vinod P. Dr. Vinod P is presently a professor in Department of Computer Applications at CUSAT. He was a postdoctoral researcher at the Department of Mathematics, University of Padua, Italy, where he implemented the EU H2020 project named Tag It Smart. He was also a postdoctoral researcher at Malawi National Institute of Technology under the IACA project on mobile security. His areas of interest include adversarial machine learning, malware analysis, context-aware privacy-preserving data mining, ethical hacking, and natural language processing. On behalf of everyone, I welcome you, Vinod sir, to deliver the talk.
Thank you for a nice introduction. Maybe is my screen visible?
Yes, sir, it's visible.
Okay. So good morning, everybody, and good morning, the organizers of the workshop for inviting me for delivering a talk. So primarily, today we will be looking at the security challenges in the IoT devices in the perspective of malware detection. So the talk would be an overview of the research activities that the group I'm involved in University of Padua, that is the Spritz Research Group, does, as well as the few glimpses of research that we have done on detecting malware, specifically on the desktop systems, the Android systems, as well as the IoT devices. So first we understand about the OWASP IoT vulnerability, the top 10 OWASP vulnerability. So if we look at the top 10 vulnerability, the first severe vulnerability that is still found in most of the IoT devices are the weak guessable or hard-coded password, which means that the most of the device, they come with a default password which could be easily brute forced, which are easily publicly available. We Google it, it would be available in public dictionary, and sometimes the password are wrongly written such that they are not changeable. So we say it is unchangeable credentials. So what happens is it grants an unauthorized access to the systems by the adversary. The second vulnerability that is usually found in an IoT device is called as an insecure network service. For example, we can say that FTP port on a device is open, an SSH connection is open, or a telnet connection is open. So what happens is most of the systems are exposed to the internet, and at any point of time, the system may be compromised, which could actually pay for the confidentiality, integrity, the authenticity and availability of the information. So it gives an open forum for the attackers or an adversary to compromise the machine. The third one is an insecure ecosystem interface, which primarily happens because of the interfaces like web, the backend API, the mobile and cloud. And the common issues that are prevalent is the lack of authentication, lack of authorization, lack of weak encryption, and lack of, let's say, input and output filtering. And the fourth most common vulnerability that is found is called as the lack of secure update mechanism. So, which is basically due to the lack of firmware validation on the devices, the lack of secure delivery, which is an unencrypted traffic in transit, the the lack of rollback mechanism, the patches that we get for all these IoT devices are basically in the clear text form. And the fifth vulnerability is the use of insecure and outdated components. So in this, it has been observed that most of the IoT devices, they run on the outdated software, which is not patched. They make use of insecure library, which gives an open area for the attackers to compromise the devices. The sixth IoT vulnerability that is found is called as insecure privacy protection. So the information that is stored on these devices are vulnerable. They can be compromised. So and also people have been inferring lot of data by the traffic, even if the data is encrypted. This we will be looking on today. So the ecosystem that is used is insecurely, improperly, and without permission. And the seventh one is insecure data transfer and storage. So what happens is that there is a lack of encryption or access control system over the sensitive device anywhere within the ecosystem, including when it is resting on the device, or whether it is transiting or during the process. So which is one of the very critical issue that is prevalent with any IoT device. Then we have lack of device management, which means there is a lack of security support when the devices are deployed in the production. During the asset management mechanism, update management mechanism, or secure decommissioning. So all these are the different weaknesses that we find in the lack of device management. Then we have insecure default settings. For example, a bad file system, a file system is being exposed with some permissions, where there is a read, write, execute permission, okay, for a particular service, which should not happen. And finally, there is a lack of physical hardening, because that means the secure boot is not enabled. So these all things will give away a lot of backdoor for the attackers to compromise the system. So these are the top 10 OWASP IoT vulnerability that have been listed in year 2021. So basically, we understood that the vulnerability exists primarily due to the service that is running, uh, the application that is there, or there is a lack of update mechanism that is happening in these IoT device. So primarily, attackers have been using malware as a vehicle to launch an attack and exfiltrate vital information from the system. So fundamentally, if we want to understand what malware basically comprises of two words. The first one is called as mal, which means something that is malicious, and where it could be a malicious software or hardware. So the primary intention of an attacker over here is to have the adversary get a potential point in a system from where he or she can exfiltrate information. So we can say that it's an umbrella term which encompasses the malicious softwares like viruses, worms, trojans, and they are the set of instructions primarily written by the attackers to deliberately infect the machine. So this is one of the very famous service which is called as Virus Total. If you can simply Google virustotal.com, and you can see that the Virus Total statistics says that the highest number of samples that are submitted is called as Windows Win32 executable. So what is this service? It's an, you can imagine it has an online antivirus engine which runs approximately 60 antivirus engine in the background. So where we can submit a sample, and it gives us a report whether a sample is malignant or whether it is a goodware or it's a benign. So we see that the largest number of samples that are submitted by the security researchers, or it could be an attacker, whether when he wants to deploy his file or launch an attack to a system, is called as Win32 followed by Android and PDF. So ideally, our focus of research should be on the first three zone, where we find that most of the samples in Windows utility are getting infected. Also, if we talk about Linux, we have an executable linkage file format, which is the default file format for any binaries in Linux, which is primarily been targeted by the attacker. So, next, if we look at what is the process of malware analysis. So malware analysis primarily means that it's a process of dissecting the malware to understand the root cause of the malware. What is the functionality of malware? What is the origin of malware? And finally, the impact that the malware is going to create onto the machine. Fundamentally, we have two ways of analyzing a malicious sample. So the first approach is called as a static analysis. In the static analysis, what we primarily do is we investigate the malicious footprint by just scanning the source code of the malicious sample. So if we are scanning the malicious source code of the sample, we are primarily looking for some suspicious set of instructions. The malware is having some set of permissions. In case of an Android, some set of malicious APIs. So our primary focus as a defender is to identify the malicious footprints that are available in the application. So definitely static analysis is fast, but at the downside, the static analysis has got a fundamental problem that if the code is encrypted or if the code is obfuscated, what will happen is that the static analysis will fail. So there is another form of an analysis called as a dynamic analysis. In case of dynamic analysis, what we try to do is we try to take the malware and run it on a sandbox. We can imagine it as a container, and this container is separate entity corresponding to our host machine. So what happens is when these samples are executing in the sandbox, it is infecting the vectors or different areas in the machine, the sandbox, but the infection traces will never, or the infection will never peep into the host machine. So it's an isolated environment. But the problem of the dynamic analysis is that the dynamic analysis is slow, it is resource intensive. So now there are many research where people are working on the combination of static and dynamic analysis. And traditional way of detecting any malicious sample is basically using a signature based mechanism. A signature may be a malicious footprint. We can imagine that it is a combination of the sequence of bytes, and if this sequence of byte is present in one or more sample, we will say that the given file is suspicious. But the downside of the signature based detection is that imagine that if we are having 1000 malware, we will be having 1000 signature. And as we know that the malware is growing and it is proliferating day by day, so the signature repository will scale up. So it is difficult for us to maintain a huge signature repository basically on a small device like small device IoT devices. So, and also signature preparation requires an expert knowledge, which is something very difficult. So ideally the signature based detection approach, even if they are followed, what we try to do is that we try to refine signature such that if we are having, let's say, a malware belonging to a specific family, let's say there are hundreds of malware which is belonging to a specific family. So people try to represent these 100 sample using set of 2-3 signatures. So that is something people are working on. using certain sequence alignment techniques. So recently, there is a profound research that is happening based on machine learning using malware detection. So why machine learning has been used in this field? Because we have witnessed that machine learning have been used in different domains. Particularly, it has witnessed its popularity in the domain of computer vision, natural language processing, and they are basically systems with providing high accuracy, intelligent as well as scalable. And the shift of the on the application of machine learning on malware detection happened because there are basically increased number of malwares available for the research community, which are basically labeled. So we can collect the malware samples either from the well-known repositories called as virus share, VX7, Contagio Mobile Dump, Virus Total. In fact, Malware Bazaar is also available, but we have to sign an NDA to get these samples from these sites, and so that we sign that we do not spread this malware through internet. Also, we have witnessed that the computational power of the existing system is increasing day by day, and they are becoming cheaper. So what happens is, when we want to create a model, a light model, or a model that has to be deployed on the cloud, the training time is now decreased. So this is one of the reason why machine learning has found a place in case of malware detection. But also, when we need to use machine learning specifically for detecting any malicious software, there is a detailed machine learning pipeline starting from dataset collection to the pre-processing of the feature. And then we try to extract relevant attributes which says that a particular sample is malicious, okay, or which also says that a particular sample belongs to a class of ransomware or virus, which is called as a multi-class classification. So feature extraction and feature engineering is a very critical problem in case of machine learning, and it is definitely a time intensive task. So and also it requires domain knowledge expert. And as we have witnessed that the computation power of the systems are growing day by day, people have been now investigating the use of deep learning architectures for detecting malicious code or malicious software, because in that case we can use the deep learning network model as a black box, and the deep learning model itself will try to find out significant feature that may be used to attest a given sample as malicious or legitimate. So once a given sample is available with us, what we have to do is we have to focus on extracting certain features. So first we try to decide what type of analysis we will be doing. Either we try to do a static analysis or we do a dynamic analysis. So as I said, if we are performing a static analysis, we are not going to run the sample on a machine or a device. So it means that our device will be infection free. So in case of static analysis, we can extract numerous features. In fact, we can have the amalgamation of these features, and the features that could be extracted are called as the strings. So the string is actually scanned through the file to find out whether we see the name, whether we see a specific URL, or whether there are certain hard-coded IP address that is present. Sometimes the authors, they try to write, the hackers, they try to write the name, unknowingly try to write the name of their group. So all those things are found, or could be some constant string pattern which could be representative of the signature. Or at the low level, the analysis can be done on the bytes. So we can have a collection of bytes which could be taken in a sliding window fashion, which is called as an n-gram. So we can have a byte n-gram. So if we say a byte n-gram of size 2, that means we are considering 2 bytes in the sliding window fashion. And people also have been investigating on representing bytes in the form of a pixel, and finally converting a malicious file in the form of an image and applying an image processing technique or image classification approach for detecting malicious samples. So this we will be discussing today. Also, at the low level, what we try to do is we take the malware sample and we reverse the malware sample using the reverse engineering tools called as the disassemblers. So we make use of certain disassemblers like IDA Pro, or we make use of disassemblers like the OLDGB, and try to get the assembly level in code of the malicious sample, and then try to find do a control flow analysis, or we try to also see the appearance of a particular instruction. So people primarily do a control flow analysis, and basically they apply the graph matching techniques to find out the longest path that the malware is predominantly using. Or as I said, we can also make use of certain API function, and we can also do the control flow analysis on the API function. However, if we try to execute a malware sample, we should be very careful that it is executed on a container. So there are a lot of research in which people have been preparing their own sandbox. So most of the best sandbox, especially for Windows, is called as Cuckoo. And if you want to especially work on the Android devices, which are the device which consumes enough battery, so there is a lightweighted sandbox which is called as the Cuckoo Droid. And also we can see the flow of information from one machine or a device using certain tools like FlowDroid. And primarily what we try to do is we extract the malicious footprints that are there in the memory. We look for the instruction, we look for the packets, the network packet. We do an analysis on the network packet. Also we can do an runtime analysis on the APIs call that has been invoked by the malicious sample. So what are the basic challenges of doing a malware analysis or detecting a malicious sample in case of an IoT device? So we all know that IoT device, they lack computational resources. So basically the existing mechanism, security mechanisms or solutions that we deploy for a PC cannot be directly applied on the IoT devices. It is difficult. Okay. So what we try to do in this case is that in order to have a foolproof analysis of malware on the IoT devices, it is very important to start with the open source malware. So we should have an IoT open source malware available. So where we can look on the source code of the malware, we can execute the malware. Further, we can have the analysis of the threat reports that are available in different security forums, particularly in the forums like Facebook Threat Intelligence or the Twitter Threat Intelligence. Also, we can look at the NVD data set to understand the common vulnerability exposure as well as the patches. So the only solution that is left at this stage for identifying or detecting a malicious software, especially in case of an IoT device, is either use a cloud service. Okay. And this cloud service will basically do an analysis, and it will send a light model periodically to the IoT devices, apply visualization techniques, so which we will be talking about today, or there are certain works that our group has been doing in case of power signal analysis, which is a non-intrusive way of detecting the malicious sample. So let us try to look at each one of them at a higher level perspective. So first of all, what actually means visualization? So malware visualization is the initial problem dated in year 2011 by a research group from Vision Lab, and especially from the group of Professor Natarajan. So what they hypothesized, or what they postulated, is that if we collect the executables of Windows or Linux, and then we do convert the executable in the form of a byte and represent each byte in the form of a pixel and print it as an image, there are certain similarities that are observed. So on the left hand side, you can see the two images of some legitimate samples. So these are two good samples. So you can see that in the center of the two images as well as the top region, there are certain patterns that are preserved. Likewise, malware Linux GAF GYT family is an IoT malware which is very famous, and you can see that the top portion of both the samples are identical, as well as the bottom portion of the samples are identical. Because this primarily happens because there is a study in case of malware research, that we find that the number of malicious samples that are coming each day is like so huge, that it is very difficult for the signature based detector to even catch the rapid malware proliferation. So basically, so what happens in this case is that you have a base malware, and the attackers, they try to tweak some portion of the base malware. They don't create a new malware altogether, because malware writing itself is a very difficult problem, and they try to generate malware as fast as possible because of the monetization. So malware itself, writing itself, is actually a huge industry now. So when we can represent a malware, we did an analysis on to look at the lower level whether there is a structural similarity of the malware. So basically, you can see at the top we have printed three malicious sample of the family called as Switzer gen, and you can look at the entropy of the byte. So the x-axis is like we consider the block, and we try to find out the block entropy in this sliding window fashion. So we can see that the families of Win32 Switzer has got certain variants, and most of the portion of the samples are identical. Okay, so likewise, there is another type of malware which is called as Win32 Aileron. So you can see that in the x-axis 0 to 1000, you have like these patterns identical. It means that we can represent the malware detection or classification problem as an image classification problem. So here, then we can make use of a different classification algorithm. So as I said, the first way of detecting a malicious sample is to have the analysis that basically happens in the cloud environment, because the analysis cannot be done on the IoT device because of the resource constraint. So what happened is that this server, what it does is, which is an intelligent service of malware detection, it will send the trained model, a lightweighted machine learning model, to the IoT device. Okay, and so this particular machine learning model will be running on this machine, and periodically what this machine will also do is it will push some data to the server, and the server does detailed analysis, either using a statistical analysis technique or a dynamic analysis technique that we referred previously, and then it will deliver the result to the device, and the device it can then forcefully stop the application. So this is one of the approach. So to start with, we require an open source IoT malware dataset to prepare our own antivirus scanner. So we can actually have a large number of variants of Mirai, which is already available. Then Elex Wi-Fi. Then we have the Light ADRA, and there is a large collection of the network traffic of IoT malware that is also available in the project called as Stratosphere, and there is another project called as IoT Pod project, from where we can actually collect the IoT malware source code and we can do an analysis. So if we target the malware detection problem, especially using the visualization approach, one of the benefit that we get is that this approach is agnostic to file type. So when I say it is agnostic to file type, we can use either a Windows executable, or we can use a Linux ELF, or we can use a Android file, or we can use a PDF that is running. Because ultimately what we are trying to do is that we are basically reversing the malicious samples or the legitimate samples and converting them in the forms of zeros and one. And then what we do is that we read 1 byte of information from the samples that are reversed, and then we represent the byte in the form of a pixel, because we have like 1 byte, which is like 2 raised to the power of 8. We get 256 different values. So each byte can be represented in the form of a pixel, and then either we can directly do represent this pixel and convert it in the form of a 2-dimensional image, or we can prepare our own color map or take the standard color map and convert the pixels in the form of a grayscale image, or we can convert the pixels in the form of an RGB image, or to store the semantic information between the pixel, we can create a transition probability matrix that we will be discussing now, and convert the image in the form of a Markov model, which can be then presented to a convolution neural network, which is predominantly used in case of an image classification problem to either detect a sample as malicious or legitimate, or do a multi-class classification taking a malicious sample and classify it into its respective family. So how do we do it? Like if we take a malware image and represent it in the form of the binary, like, and then we convert each binary into a numerical vector, which is having a value between 0 to 255. So what we do is the first value will will index into a row, and the second value will be indexed into a column, and the intersection there will be a pixel value that will be used to represent a pixel. So in this way, if you have a color map, you can convert each pixel in the form of an image, and take this image and then try to extract the textures from the image, or from a pattern from the image, using either a deep learning technique or do a texture analysis on an image and present the texture to a classifier. For example, the most prominent texture that usually we take in case of an image is called as the gray level co-occurrence matrix, or histogram of gradients, or the local binary pattern. So which I would not talk, because we have a limited time constraint. The second one that can be done is like, we can assume that if we have the first byte and the second byte, which is like byte I and byte j, we assume that there might be a relationship between byte and I and byte j. So what I mean to say over here is, like, if you see the top one-dimensional vector, for this one-dimensional vector, I will take the 2 consecutive bytes. The first one is 0, 1, and I will try to find out the frequency of this byte in the entire file. Okay, so then what we do is we will create a map, a transition probability matrix, which has like 255 rows and 255 columns. And then we will represent the co-occurrence byte in the form of a probability value. So you try to find out the frequency, and we divide it by the total number of maximum elements in the row. So you get a value between 0 to 1, and then you multiply it by 255 so that it becomes a pixel, and this pixel can be represented in the form of a two-dimensional matrix, which is called as a Markov image. So the advantage of this image is that it is actually storing the consecutive pixel information. So we can assume that there is some byte information that is being stored over here. And finally, once we have the images of the malicious sample with us, what we can do is we can make use of any algorithm. For example, we can make use of the conventional machine learning algorithm, which is predominantly used for images like support vector machine, or we can make use of a deep learning architecture. So I'm talking here more or less about convolution neural network, because this comes from one of our paper. So the convolution neural network, basically it has got two important function. One is called as a convolution and max pool. So this convolution and max pool are basically repeated, and finally the output is flattened. It is converted into a linear vector, and this linear vector is finally submitted to a fully connected network. And in this case, the input is the classification of animal. It will classify it as cat or dog. But fundamentally, what is the significance of using convolution, and what is the significance of using max pool? By applying convolution, basically we abide by two property. The first property is that we have some patterns in the given image, and this pattern in the image is basically smaller as compared to the image as a whole. And definitely this pattern may not be static. This pattern moves here and there in the image, especially in case of malicious file. In order to defeat the antiviruses, what malware authors they will try to do is they will try to change the flow of the program by inserting some conditional or unconditional jump statement. Basically the flow is identical, but they try to insert some bogus code, and they try to change the flow. So once they change the flow, what will happen? The byte pattern will change. So if the byte pattern changes, it will move throughout the code. Okay. And this the another important property of a max pool layer is that the max pool tries to subsample the complete image. It will try to downsample the image without losing the pattern. So finally, the output of max pool can be submitted to the convolution, to the dense network, which will basically classify the sample. So output of every convolution max pool is definitely an image. So we also have seen now that there is a large hype and popularity about the IoT, because most of the IoT devices are controlled by the Android application. So we have invariably the IoT device which is being used for smart home, in the smart vehicle. We have the mobile phone, which itself is one of the prevalent example. We have an IoT device which can be used for the industrial control system. But these IoT devices are basically controlled by the Android application. So if there is a vulnerability associated with an Android application, then that vulnerability can lead to an exploit which will compromise the IoT device as such. So why there has been a rise in the malicious samples, basically. So we have seen that the malicious samples are prevalent because there have been a lot of applications that are deployed in the well-known app store like Google Play Store, or the app stores like Nine app. The problem is like the Google App Store basically uses a weak mechanism which is called as a bouncer, which does a sort of behavioral analysis. But there has been a report that many samples in the Google Play Store is malicious, and people have been targeting to remove such applications from the Google Play Store also. But why there is a rise of application in the Play Store? Because basically the company or the Play Store, they want to give a privilege to the user to showcase their capabilities. And if we want to do an analysis, it is very important to understand the structure of a file, whether it is a Windows executable or a Linux or an Android. So in case of an Android, the complete Android file is divided into various modules like the manifest.xml, which is the heart of an Android file, and it consists of the explicit permissions the applications will be using for the installation. And then the entire Android application is available in the form of the classes.dec file, and we can reverse this classes.dec file in the form of a binary and then do an visualization approach that I discussed previously. Then we have a resource folder, which is a collection where we see that the apps, they show certain icons or image, they are present in the resource folder. Then the Android, they make use of a reference to the native libraries. So all native libraries are present in the lib. And finally, the certificates of the Android applications are present in the meta INF folder. So if we have a application, so to do an analysis and to detect a sample, we can extract features. So we can extract features from different modules or components of an Android. So basically this is a taxonomy that we created. So if we take an Android manifest.xml file, we can extract the permissions, we can extract the hardware and software features, we can in fact do a detailed analysis on intents. So intents are basically the message passing mechanism in an Android application, within an application and across an application. So we can actually check for the source and sync pair. Okay, so we can also do an analysis on services, broadcast, receivers, and action. If we do in-depth analysis on low-level feature, so we take the Dalvik code, the dex code, which is the classes.dex, and we try to reverse the classes.dex to get the smally files. So you take the classes.dex and you reverse it, you get lot of files which are called as smally files, and open each smally file and try to extract the instructions from the smally file, do the analysis. People also have done an analysis on thinking that the number of smally files in case of the malware is more as compared to the legitimate. They also have done the analysis on string. We can do an analysis on application metadata based on the number of download. We can also do an analysis on dynamic features, that is system call and network traces. So we basically did collected certain 342 features by referring to the standard articles, and we collected some set of applications. We collected permissions and intent, and then we represented a file in the form of a binary vector. So each application was represented in the form of a vector. And just for your sake of understanding, I'm listing some sort of an application. So at the top, you can see the get device ID, get subscriber ID. These are the API, the send SMS and delete packages are permissions. Also, we find that the malicious application explicitly make use of certain commands like chown, chmod. So these are certain commands. So ultimately, we represent each application in form of a linear vector, which is basically Boolean. So if a particular API is present, we mark it as 1. If it is absent, we mark it as 0. And Then we submit this application vector. So on the center part, you can see the feature vector. So the collection of applications are basically called as a feature vector, and we target is it in the form of a supervised machine learning problem. And this feature vector is submitted to a one-dimensional light-weighted convolution neural network. And the convolution neural network makes use of multiple filters. So the filters are nothing but it is taking the features in the sliding window fashion and some max pool layer, and finally submitted to the deep learning model for classifying, for identifying whether an instance is normal or whether an instance is malicious. So here we did an analysis on the botnet traffic analysis. So I will talk about the data set that we took and the architecture. So our architecture had got two convolution layer, and we had two max pool layer, and the input dimension was 342 because our total number of features were 342. And the boxes that you see, the different colored boxes, they are the filters that strides over the one dimensional vector. So we collected the data set from the UNBCAC, which is a very famous Canadian university. You can just visit this website to get lot of security related data, especially for Android or for IoT, specific to the IoT or for the smart grids. And we collected approximately 1900 sample with 4800 samples separately collected from Google Play Store. And then we did a detailed analysis on the impact of the number of filters, the length of the filters, and then we compared the standard convolution neural network which was running on the cloud to the machine learning algorithms which the researchers have investigated. So we tuned the hyperparameter and we found that 32 filters gave us the highest training accuracy of around 98%. The length of filters was 98, and the max pool uh, uh, ratio was actually 2. So basically taking these hyperparameter, we submitted the unseen samples, and then we detected the unseen samples in the test set. And we can see that the convolution neural network had a highest F1 score of 0.98 because the data set was indeed imbalanced, followed by the linear SVM with 0.97. Further, we also did a comparison. This I will leave with the state of art approach. So the problem with the static analysis, as I said, is that they can be easily deceived by the attacker. So we extended our work on dynamic analysis. So when we say dynamic analysis, we have to run the sample on an emulator. So we took the emulator and we executed the sample in an emulator. So basically we create a device, Android device first, and we will launch the application on an Android device. And then what we do is we take use of a Linux utility called as an strace, as well as we make use of a tool called as the Android Monkey. So the Android Monkey is basically a first testing tool. What it tries to do is it will try to submit random number of swipes, gestures. So the application will feel that it is interacting with human. And in that case, we recorded the system calls like open, connect. So the application is directly interacting with the operating system, making use of a system call. So this is so the strace utility basically requires the process ID of an application, but the Android Monkey basically requires the package name. So we submitted, we changed the location, we changed the battery power so that the application indeed feels that it has been interacted with the human. And then we collected certain set of system calls. So just to show you that we plotted the distribution of system calls in the legitimate set as well as the benign set, and we can see that there is a huge dissimilarity. So if there is a huge dissimilarity, so it means that we can use system for call for the modeling purpose. Especially we see that there is a huge dissimilarity when we take the consecutive pairs of system call. So we took the consecutive pairs of the system call and we submitted it to a deep neural network architecture with the collection of data sets. So this data set is very famous, which is been available for download. And we can see that the deep neural network architecture gave approximately like 98.3% accuracy in classifying the identifying the malicious instances. Now I come to the last part of my talk. So we saw two types of analysis, particularly one analysis which is primarily dependent upon the cloud. The second part is saying that we do an analysis without the knowledge of features, so we can use the visualization approach. The third and most important form of the
Sir, uh,
approach that we are
sir,
in, yeah.
due to time limitations, will it be okay to wind up in 5 minutes?
Yeah, yeah, I'll wind up, wind up. It's last couple of slides. So we can do the power side channel analysis. So power side channel analysis means that you are trying to measure the power consumption of the device. So when a device is running malicious sample, what is the power consumption? When the device is running a legitimate sample, what is the power consumption? But the challenge is that the power signals are noisy, uh, and the only solution for this approach is to learn the power signals by running the open source malicious software to understand the difference between the peaks. So if we look at the power signal analysis of the Mirai malware, which was actually planted on the D-Link IP camera, so we can see three windows which are marked in red color. So the first window is actually a login attempt. The second window is an environment preparation, and the third window is the file download. So definitely, if we try to train our machine learning model with these windows, basically we can identify the type of attack that is happening. So we investigated on the open source malicious samples, and we found that these are the commands that are predominantly used by the sample. So as you can see that most of the malicious sample make use of a wget command, which means it wants to try to download something onto a device, then it changes the permission, it executes the malicious sample, and finally and it will remove the malware samples from the system so that the defenders or antivirus solutions will not understand. So the attack that primarily happens is can be summarized with this. So basically there are three phases in the attack. One is an intrusion phase. So in the intrusion phase, what an attacker tries to do is it will try to it will try to attempt to log into a system by looking at certain vulnerabilities. We can assume that the device is having some weak or default password. So the attacker will try to get into the system by cracking the password, either using a brute force attack, or it would do a dictionary based attack. Then the infection process starts, and in the infection process, the first task what a malware does is it will try to prepare the environment. So by preparing the environment, the malware is trying to execute a ps command or a dir command to try to find out an vulnerable application that is running. So once it has found the application, what it will try to then do is it will try to download a file using the get command. It will try to contact using an encrypted traffic to a remote server and try to download the binary. Slowly, it will change the permission of the binary file using the chmod command. It will execute the malware, and then it will remove the malware as a whole from the system, so that only the traces are left, but the antivirus solution will not understand that it is infected. So what we try to do is we try to understand the power signal. So through power signal, what we did is for each type of instructions that we execute, we try to measure the power signal using a deep learning architecture called as an autoencoder, which will take an input and try to find out the latent information which are representative of the features of the malware. And then in the decoder part, what it will do is it will try to regenerate the signal. So basically the optimization problem is you have an input I, and you want to minimize the difference between the input I and the decoder output, and lambda is the regularization parameter. And then the challenge was that the signal are noisy. So what we do is we perform the simple moving average, basically 100-point simple moving average. We consecutively take the samples and then we average it. What will happen? It will remove the small fluctuation. We can also perform the wavelet denoising because it will remove the strong noise that is initiated using AC power, and we convert the signal into the MEL spectrogram, and this MEL spectrogram is then submitted to a deep neural network architecture to find out the patterns. Finally, uh, uh, what are the open research issues in this area where we have security challenges and detection of malware? First of all, there is a class imbalance problem. That means the number of samples of malware for a specific family is less. So how do we tackle this? You can make use of some network called as Siamese neural network, which is predominantly used when we have a lesser number of samples for training. A lack of open and benchmark repositories available. So definitely then it will use the manual labeling. Then there is another problem called as a concept drift. There is a myth that we create a model in year 2000 and we feel that it will detect sample in 2020. It doesn't happen. You have to periodically train this. Then we assume that the training model and the test sample have an identical distribution. So there is a very important area that is coming on, which is called as adversarial machine learning. Also, samples are very well intelligent to understand the analysis environment. So that also can be done to do an analysis of identifying a sample which detects an evasive environment. So I finish with my talk, and maybe we can take a few questions if all we have.
Sir, you have two questions in the chat box. Shall I read it out for you?
How to overcome the problem of insufficient uh, privacy protection is one, and what are the generic standard that needs to be followed in applications like smart grid. Okay, so I will first of all try to answer to few questions that has come. First of all, the first question about the privacy part. The only answer to the privacy preserving part is that you have to come up with an architecture. First of all, never believe on what is running on a cloud. You should not even believe on a cloud. What we do is that the client submits some information to the cloud, which is in the form of encrypted information, and the server should compute do an analysis on encrypted information using certain homomorphic encryption scheme, which is called as privacy preserving technique. That is, you submit an information in the form of an encrypted form, and the server will do an analysis on the encrypted data using certain homomorphic encryption. Okay. And secondly, another question that I see is that what are the general security standard that needs to be followed in IoT applications like smart grids. So basically, when we want to prepare a security system, we have to be making use of a system which is called as a proactive system. A proactive system is a system where the designer basically tries to mimic the action of an adversary and prepare it. And ideally, what we should try to do is you should have a very close look at the OWASP standard. And whenever you try to build a system, you try to stress test your model against the OWASP standard. At least the 60% of the OWASP criteria should be fulfilled. So that is the only answer to it. Whether we create an Android-based security system, we create a security system for smart grid, or specifically for an IoT, or specifically for a web, we should look at the OWASP standard, and then we try to see that whether the OWASP standard uh, is like fulfilled or not. Okay, so that is the only way we can address the issue. Is it fine?
So, sir, shall we wind up the session?
Yeah. Thank you.
So, let me say that this was a wonderful presentation, and in fact, this the first presentation in this FTP that extensively talks about security. Actually, many of the participants had several questions earlier regarding security, and I think most of them have been addressed in this presentation. I think if we had more time, we could have gone in depth into some of the more aspects that Professor Vinod was discussing. So definitely it's an eye opener, and it has cleared several doubts regarding how to implement security in IoT devices. And I think this presentation will go a long way in thinking about security while we design our IoT applications. So let me take this opportunity to thank Professor Vinod on behalf of the organizers as well as all the participants. Thank you, sir, for the wonderful presentation.
Thank you so much for the opportunity that is given. It was just a glimpse. Maybe I would request all of you to look at the latest papers in Usenex or CCS to understand the state of art. And if there is anything that I can do, you can just look at you can write to me. My email address is already shared. I look for collaboration. Thanks for patient listening, and thanks for the opportunity. Thank you. Shall I
Yes, sir.
leave then? Thanks. Shall I
Yeah.
leave?
Thank you. Thank you, sir. Thank
Thank
you.
you. Thanks.